Welcome to Lecture 6. This lecture is going to be on proton exchange membrane fuel cells. And this time we're going to be going into details that we haven't been going. So far we've stayed pretty high level on some of the thermodynamics and the irreversible thermodynamics. Now we're going to go into detail of what will be the PEM fuel cell, which is being used in a lot of low temperature applications. And as we'll see here, there's a lot of PEM applications, anywhere from car to backup power to almost all portable devices are some derivative of proton exchange membranes, either operating off of like hydrogen or methanol. And to give you a feel, for car applications, the typical scale is on the order of 100 kilowatts, maybe 80 kilowatts on a smaller scale vehicle to maybe up to 120 on a larger mid-size car / small SUV. Backup power generation is often being used for cell phone towers, and that's on the order maybe 1 kilowatt or so. Most of the portable applications, if it's your cell phone, we're talking about 1 watt. If it's your laptop, we're talking about maybe 10 to 100, maybe 10 to 50 watts. And then we've also got another application that's taken off is PEM-based forklifts. And as I've said before, this is taking off because you can't be using diesel forklifts inside of certain factories where the workers would have to be breathing the exhaust. So the choices are either going to be a battery or a fuel cell. And depending on the application, I mean, both are viable. Just a question of whether or not you need more range, then you're probably going to go with the hydrogen one. And that's a range, or if it's a fill time is an issue, that'd be another reason to go to hydrogen rather than a battery. And then you're going to have you can also use PEM fuel cells for other portable power, but on the 50 watt scale, if you want maybe something extra power in your RV, or this is being also used for military applications if you need like a 50 watt power source. And here's a kind of a zoom in on the Honda's FCX. This is a fuel cell vehicle that you can lease in the Los Angeles region, and it's a 100 kilowatt proton exchange membrane fuel cell. It's also got a lithium-ion battery pack, right? So it's a fuel cell and battery car. It's a hybrid. And on all these, not only are they going to have fuel cells and batteries, they're probably also going to have some kind of capacitors, so that the capacitor giving you the very quick response, batteries giving you stuff on the minutes, and then your fuel cell basically is giving you the hours of range. And the total range on this vehicle, is based off of the size of the tanks. And for this particular vehicle, they've sized the tanks to give you about 300 miles of driving. You could you make the tanks larger if you wanted more range. That's just the size that they picked. And just want to note that it turns into, storage-wise, it's only about 4 kilograms of hydrogen at this at like 350 atmospheres of pressure. The storage tanks themselves weigh a lot more than 4 kilograms. I don't know the exact specifics, but typically the weight ratio between hydrogen and the rest of the storage device is about 5%. So if it's about 4 kilograms, we're talking probably on the order of 80 kilograms of actual weight for the storage tank itself. I do want to point out that in the LA area is LA is the location in the U.S. with the most number of publicly available and or privately available hydrogen refueling stations. Currently, as of this recording in October 2012, there's 8 public stations, 15 private stations, and 14 stations in development just in the Los Angeles area. After LA, probably the second largest number of stations would be in the San Francisco area, but there's only about 1 publicly available and then a couple privately available ones San Francisco, Sacramento region. Other than that, it's kind of like hit or miss throughout the U.S. on whether or not there's a hydrogen station. And one thing to remember, it's a good thing to keep in your head, back in your mind, is the chemical enthalpy in 1 kilogram of hydrogen is about equivalent to the chemical enthalpy in 1 gallon of gasoline. So it just gives you kind of a quick feel. Now, of course, hydrogen is being used more efficiently than gasoline is being used, which is why, as you notice here, 4 kilograms of hydrogen gives you about 300 miles, whereas 4 gallons is not likely. 4 gallons of gasoline is not going to get you 300 miles unless you're on some unless you're getting on the order of almost 100 miles per gallon, which is not really viable. So you can see that that's one thing that's happening here, is that a kilogram of hydrogen is being if you look at the system efficiency, it's some kind of miles per chemical enthalpy. You're getting a higher system efficiency, miles per enthalpy, from hydrogen than you are from gasoline. But normally, when you look at overall well-to-wheel analysis, normally you find that these things normally are about pretty similar, or maybe a little bit because obviously the hydrogen had to come from someplace, right? So depending on where the hydrogen is coming from, that can affect your overall well-to-wheel analysis. And as I said before, the system efficiency, I mean, it's good. You obviously want it high, but the real metric is going to be some kind of levelized cost per mile driven, right? Levelized, where you account for capital costs and fuel costs and any operating and maintenance, and you kind of use some kind of discount factor, time value of money, to turn it into a levelized cost per mile driven. So that's what, when we get to the economics in a couple lectures from now, that's what we'll be looking at with cars, is calculating levelized costs per mile. Okay, so we've said these before, but it's good to reiterate. What are some of the advantages and disadvantages of PEM fuel cells? It's not that any of the advantages or disadvantages are going to either make or break them, right? You have to compare, as I said before, on that levelized cost per mile driven, right? Because that's what people want to know. How expensive is it for me to drive a mile, when you have to include the loan, how much I'm paying on a loan, how much I'm paying for fuel, how much I'm paying for maintenance. But these are kind of the general advantages and disadvantages. Advantages being very high power density compared to other fuel cells. Nearly as high power density as in combustion engines, reciprocating combustion engines. Very rapid startup. Right? These are low temperature. They'll actually start generating electricity almost immediately, because even if they're not fully warmed up, they'll start be producing some electricity, and then that amount will increase as it starts warming up. Fairly lightweight. I mean, a large portion of the fuel cell is actually carbon, if you use carbon plates, or carbon or steel, and polymers, which are also largely carbon-based. So we're not talking about very heavy materials. It's also quite porous, so a lot of it's just air, or fuel and air. And low temperature means it means a couple things, but the advantage is it's actually we're able to use polymer materials for the electrolyte, and it's fairly easy to seal. And because it's also low temperature, you don't have issues as you do in high temperature fuel cells, that you'll have different materials increasing in scale, or increasing in size at different rates. Whereas if you're operating at low temperature, nothing is really expanding or contracting significantly, other than maybe the membrane as it humidifies. So then let's discuss some of the disadvantages. Okay, disadvantage is because you're operating at low temperature, you're going to have to be using some really, really good catalysts. And catalyst development is becoming I'd say the development of catalysts is getting better and better with time. So this is becoming less and less of an issue. Now kind of the best platinum catalysts with like nickel, mixed with nickel or mixed with other materials, are getting to the point where it's not swamping the overall costs. A few decades ago, the cost of platinum was the largest cost in going into the fuel cell. And now that is, we can say that platinum is no longer the highest. It's now just becoming one of many costs in the fuel cell, like bipolar plates, the membranes themselves. Like platinum is just becoming another one of those costs. Yes, and it's getting to the point where the amount of platinum that you need for your PEM-based fuel cell is about equivalent to how much like ruthenium you'd need on a catalytic converter. So you could, if you compare ruthenium with platinum, in some ways you're saying you still need platinum metals in cars because of the catalytic converter. So we're now getting to the point where the amount of ruthenium you need in a catalytic converter is about the same as the platinum in a fuel cell vehicle. So it's not like we're going to be having to start mining a significant amount more platinum metals just because we're going over to these platinum fuel cells. And this is a good thing because if you know, in the recent news at least, there have been a lot of strikes in South Africa at platinum mines. So this is something that definitely is something to look at. If you can reduce the amount of platinum, then you reduce your basically dependence on specific mines across the globe that mine platinum. Okay, so another disadvantage is that because it's low temperature, the thermal energy that's generated has virtually no exergy. And it's almost worse than that. Not only does it have no exergy, which means you can't get any work from it, but you actually have to get rid of that thermal energy. And getting rid of it when there isn't much of a driving force normally actually ends up consuming work. And so you have to put in heat exchangers and be flowing through oftentimes different liquids that you need for heat removal. And so you've got to have some kind of compressor to kind of to have basically a recirculation loop, which will drive thermal energy out of the PEM vehicle over to some kind of radiator. So not only do you not get to do any work with that thermal energy, but you actually end up having to spend work to get rid of it. And then another disadvantage is that you have to be pretty stringent on the amount of carbon monoxide that gets into the anode gas stream. And there's ways of getting around this, either through putting smaller amounts of air or mixing platinum with other metals, even ruthenium. There's ways of increasing the purity requirements, but still what it does is it forces you to do some, I'll say, minor to major system changes, and it makes it quite difficult to be sending reformed hydrocarbon fuels directly into fuel cells. There's ways to do it, and especially now that there's hydrogen separation membranes, which are 99.9999% pure hydrogen. This is probably not as big of an issue now that we have membranes that are nearly 100% selective for hydrogen, which means you could have fossil fuels even being reformed on your vehicle itself, as long as it's going through some kind of hydrogen separation membrane before it gets to the fuel cell. And what happens is with carbon monoxide, it sticks to the platinum and basically takes away a site in which you could have a reaction. Okay, so here's a good visualization of what's going on in the fuel cell. The green here are the bipolar plates. So imagine the plate is actually bipolar, which means that a single plate would have both the air and hydrogen channels. So you could almost imagine this being stacked. They're stacked one on top of each other. So in this case, we'll show air is going through the air channel, and then what happens is there'll be a gas diffusion layer. This is a porous carbon material. We'll show in the next slide. And then after that, you finally get to your catalyst layer. So this would be the cathode catalyst layer in the dark brown. The light brown, reddish brown is the gas diffusion layer. Dark brown is the actual catalyst layer, and then shown here, kind of this water visualization, is actually the membrane, the polymer electrolyte membrane. And then you're going to have, once again, your anode catalyst layer, your anode gas diffusion layer, and then your hydrogen channel. Okay, so here's we're going to show that same kind of schematic, but we're going to walk through kind of the steps now. All right. So what we have is the cathode channel on the top, anode channel on the bottom, and so we have the half reactions going on each we have the half reaction where oxygen is consuming electrons, and then on the hydrogen side we have hydrogen turning into protons and electrons. Here's the membrane, catalyst layer, gas diffusion layer. And that's that bipolar plate, which is it's basically acting as the form around the flow channel, and it also needs to be electrically conductive because electrons have to, when they need to be able to go from as they get consumed, they're getting consumed as basically electrons flow from the anode to the cathode. Right. And then they get consumed at the cathode. And the current is being carried by protons. And then once again, from the anode to the next cathode, it gets carried by the electrons. So the current plate has to be electrically conductive. Right. This is kind of to visualize what I was saying before again. The electrons, when we say they leave the circuit, that's for the very last anode and the very last cathode. When you put them in series, that's where it goes through your load. But when you stack one pair of anode cathode on another pair of anode cathode and stack, what's happening is really the electrons are going from the anode, from the anode electrode through the anode gas diffusion layer, through the bipolar plate, into the next bipolar plate where it goes through the cathode gas diffusion layer into the cathode electrode. So here's a diagram for the air flow, hydrogen flow, right? So air has got to be able to go through the channels. Oxygen has to get through the gas diffusion layer to the cathode electrode. Water has to leave the cathode electrode, go through the gas diffusion layer, and then get kind of picked up in the air flow stream and pushed along through as kind of either droplets or slugs. Right, so the air has a double duty. One, you need to get the oxygen to the electrode, and then you need that pressure from the air to force out water so it doesn't build up in the channels. And on the hydrogen side, right, you're supplying hydrogen. It's not as difficult to get the water. There will be some water on the anode side because of some back diffusion processes, but most of the water is being generated. But the water is being generated at the cathode. It's just that some of the water could back diffuse into the anode, so you may need to supply some hydrogen pressure to force water out on the anode side. And as we've seen before, you can make voltage current curves, and you can step through normally the largest source of irreversible the source of overpotential, irreversible or overpotential, is due to cathode activation. It's the slowest, it's the rate limiting step, you could say in some sense. Anode activation is that linear term, and you can increase or decrease that portion. As you go out to higher and higher currents, that this becomes larger and larger. Anode activation, is small compared to the cathode. Ohmic is the one, Ohmic is the one that can start dominating at high currents. And then, of course, if you're close to the limiting current, you're going to have the mass transfer. So now we're going to watch a little bit of what happens with fuel cell flooding. So the first thing that happens, let me go back. First thing that happens is the membrane itself is, let's say, a little bit dry, and as you start running some current through here, you start producing some water, and the first thing that will happen is that the electrodes themselves will start flooding. And then if you continue to create current faster than it can get out of the system, you'll start forming water droplets in the channels. And you can eventually get to the point where you're producing so much water that the channels themselves completely flood, completely blocking off the ability for oxygen to get to the cathode. And that is one way in which your voltage will just start quickly dropping. And that's a form of mass transfer over potential. What happens is oxygen just cannot get to the electrode fast enough because it just can't get through the channels, and then it can't get through the gas diffusion layer. So here are some more ways of visualizing what's going on. Graph in the upper left is kind of what we've already shown. Now what I want to do is kind of zoom in on what's happening at the catalyst layer. So with one way of visualizing what happens at the catalyst layer is you have these kind of spherical carbon particles, and on top of the carbon particles are going to be very small platinum particles, maybe about 3 nanometers in width. Carbon particles are maybe on the order of 40 nanometers. And so what's happening at these sites, right, let's say for the cathode side, we need to get oxygen to the platinum, where the oxygen has to then adsorb onto the surface, split into atomic oxygens, and then start grabbing some electrons and grabbing some protons. So how did the electrons get there? Well, the electrons get there, they've got to travel through this kind of maze of carbon particles, right? So that's how they're going to be able to get from the gas diffusion layer to the platinum particles. So electrons have just kind of work their way through this maze of carbon particles, which means that you have to have enough carbon particles so that you reach some kind of point at which you have a path through the entire system. It's kind of like a percolation threshold type of parameter. Once you get to about around 30% of it being filled with carbon, you'll have ability to conduct electrons through the whole thing. Whereas if you only had maybe, it's a very non-linear percolation, if you've ever seen, is very non-linear. If you have 10%, you have almost no electrical conduction. 15%, almost none, and then you start getting into 20 to 30, and it just starts really rapidly rising. Okay, so how do you get the protons in there? Well, the protons have to come in through naphion, which is it's the same as the electrolyte. So your electrolyte actually extends out, think of, into your electrodes. So we've got naphion, kind of has to be close enough so that it can get a proton to go onto, so they can be close enough to platinum somehow. But remember, we also have to have the platinum exposed to oxygen, so the oxygen can get there. And then, so once the oxygen grabs an electron and protons, it will make water, and then that water's got to be able to get out of the system. Some of the water can leave as water vapor, in which case it's fairly easy for it to leave. But you can see if it's leaving as water vapor, and we're at 1 atmosphere, the higher water vapor concentration you have, it's going to eventually start eating into the amount of oxygen, which means that your rates will start dropping, or as we saw either from the Butler-Volmer equation or from the Nernst equation, the Nernst potential. If your oxygen starts dropping and your oxygen starts dropping and water vapor starts increasing, you're going to start losing voltage. So really what you need is some kind of like triple, and you can call this a triple phase, or you can call it like a quadruple phase, right? You got to have a point where electrons, protons can meet, and then you need reactants to be able to come in and out also. Okay, so now let's start talking about the gas diffusion layer. Now this is just kind of a zoom in to give you a feel for what it is, and it's going to be a porous carbon paper. Sometimes it's like either woven, but it's just a material that's going to allow electrons. It's got to be electrically conductive, so it's got to allow electrons to move through. It's also got to allow oxygen to get through, and it's often coated with Teflon to make it hydrophobic, so that you're not having droplets of water. That keeps it kind of in the keeps water more in the gaseous phase as it leaves. Okay. The thing, because flooding is a major issue in these low temperature fuel cells, how you design the channels is really important. It's not going to be important for that. It's not going to be that important for high temperature fuel cells, but it's very, very, very crucial for low temperature fuel cells. So you can have there's a lot of different types of designs you can have, but I just want to give you a feel for what they're called. You can have a parallel channel flow, and it's pretty straightforward. You have a large number of parallel channels. So what you can see here is, right, if you have a large number of parallel channels, the gas, the velocity in any one of the channels is not very high compared to a serpentine case, in which you have one channel that weaves its way throughout the active area. Okay, so in this design, that grayish color you can think of as your active area electrode, right? And these are your channels. So this is when we normally say area, we're talking about the area that we're seeing here. And so a lower velocity in the parallel case compared to the serpentine case for the same overall flow rate, where overall flow rate would be, say, some volume of gas going there per unit time. Okay. Because the cross-sectional area in the parallel case is the number of channels times the area, cross-sectional area of each channel. Where cross-sectional area is a little bit hard to see here, but it's what's kind of coming out of the page. It's easier to see in some of the other ones. It's the area, cross-sectional area that of the channel itself. So in the serpentine case, you only have one channel in the same cross-sectional area. It's the same cross-sectional area as in the parallel case. But because you have a lot more channels in the parallel case, what it means is your overall velocity is less. And what that'll mean is you'll have, if there were no liquid in the channels, your pressure drop in the parallel channel case would be a lot lower. So you'd think you'd want to go to this way. But the problem is, if you have less of a velocity, it's harder to push out water. It's harder to push out liquid water. So there's reasons to go to serpentine channels. Even though you may have a higher pressure drop, you need that higher pressure drop to force out water in some cases. So the optimal design is going to be someplace in between the two. But just want to give you a feel The parallel ones are going to be poor for liquid water, but lower pressure drop. Serpentine are going to be better at removing liquid water, but you pay the price because you're paying for it in a higher pressure drop. Right? And obviously something has to supply that higher pressure, right? Some kind of compressor, and it's going to start eating into what we call it. It's a parasitic load. It starts eating into the voltage that you're getting from your fuel cell. Right? Okay. So another issue that has one is where you got to find some kind of optimal is how much water should be in the membranes themselves. If it's too dry, you're not going to be able to get as much voltage out of the fuel cell because your ohmic resistance starts going up. The membrane needs high humidity for conductivity. So you can get to the point where the membrane's too dry. You can also get to the point where it's too wet, right? Because if it gets too wet, then you're getting flooding into the channels, into the electrode. So there's going to be some kind of just right, and that right will be you need enough water to get high conductivity in the membranes, but too much gives you flooding. So it's a really kind of tricky, but we've largely figured out how to get the right balance. So the membrane itself, most PEM fuel cells are running using some kind of Nafion derivative, which is like a perfluorosulfonic acid. So what this is it's like a polymer. It's a fluorine-backed carbon polymer. And what they do is they put on side chains, and at the side chain is some kind of sulfuric acid group, SO3 minus, and there'll be if there's no water around, then there'll be a proton associated that's directly attached onto that sulfonic acid site. And generally these membranes are good up to about 100 degrees C, and they need a lot of hydration in order to maintain the conductivity, because as we'll see in the next slide, we need water to be able to pull the protons off of the acid group. So Nafion, it will really quickly start absorbing water if it's around, and you will see this is kind of the steps we're going to go through when it comes to how do we get more proton mobility. So at first, if you just have, let's say, one water molecule per sulfonic acid site, that water is going to be, and that proton associated with the H3O plus, it's going to be very tightly bound. And but what happens is you start increasing the amount of water. You now have a proton on a water that is more free to move around, and eventually you get to the point where that proton is fully free to move about. And this is what we mean by the conductivity increases as you hydrate the membrane, as you increase the membrane. You eventually get to a point where a proton is now fully free to diffuse around. And here's what this looks like quantitatively. If you have conductivity as a function of relative humidity. Right? It's basically tells you relative humidity is like a ratio of saturation pressure compared to the actual pressure. Saturation pressure of water vapor compared to the actual pressure of air. So that goes from, let's say, 20% to 100%, your conductivity increases that entire time. And it's not linear. It's, as you can, between 80 and 100% relative humidity, you have the largest change per change in relative humidity. So, but as we said before, if you go, the reason why you may not want to work right at relative humidity of 100%, right, there's going to be trade-offs. If you have too much water, you could start producing flooding. So a lot of times the just right might be, depends on your exact application, but it might actually be in the 80% relative humidity range. So here's just some images of what flooding would look like in the channels. On the left is a graph. I believe it's neutron imaging of a fuel cell, and you can kind of see in that the red and green locations where the channels have just become completely flooded with liquid water. Channels look like, if you look on the right, this is a 5 channels. You can think of it as 5 channel. It's a mix between parallel and serpentine. Right, it's 5 serpentine channels that work their way through the active area. And you can see some of the channels at certain points just completely flood, which means that at points only 4 of the channels are actually available to distribute air to the cathode. And this is what it would look like if you have, here's a fuel cell voltage, fuel cell versus current density, and fuel cell voltage versus current density for either serpentine flow or for parallel flow. Serpentine one here is 3 channels that work their way through, and then the parallel is about 25 or so channels. And what you'll see is that with the parallel channels, as you're going through, the voltage starts dropping compared to the serpentine ones, and that means you hit the mass transfer limit faster in the parallel one than in the serpentine case. And it's just, you eventually get to the point where the channels will start flooding. And of course, so if you wanted to figure out what should your optimal design would be, you need to look at not just the fuel cell voltage versus current density, but you need to look at fuel cell voltage minus the amount of power consumed by the compressor or something like that, right? Which we're not doing here. We're just showing you how much of voltage you lose because of being in parallel versus serpentine. And you would compare, what you'd want to do is you'd want to get the most voltage after including the power that you have to spend to remove the water, because the serpentine channel flow is going to have a higher pressure drop than the parallel channels case. And we'll be going into this later, but I just want to end this set of slides on a just general schematic for all the things that actually go into a PEM fuel cell system. And we'll get into this topic into a couple lectures from now when we look at fuel cell systems. And just want to point out here just the sheer number of, right now we're focusing on just the fuel cell itself. We're going to eventually be stepping back and looking at all the compressors and heat exchangers, radiators, ejectors, coolers, humidification units, coolant loops that you need to run a PEM fuel cell. That's all.